On October 29, 2025, right next to the blazing sun, the interstellar visitor 3I Atlas suddenly betrayed every law of physics. It accelerated wildly, deviating exactly 4 arcseconds from the orbit NASA had predicted. A tiny shift, but enough to make Avi Loeb, the father of the Oumuamua artificial hypothesis, blurt out, "This isn't a comet, no smoke, no fire, no massive gas cloud exploding, just a ghostly blue streak flaring up in the deadly red dust zone, a color no natural object is allowed to have." Cold calculations to produce the thrust 3I Atlas would have had to lose 1/10 of its mass in an instant. Or something is steering it. And what will make your heart stop? The new orbit after this mysterious course correction is aimed straight at Earth. A perfect flight path intersecting precisely in December 2025. Measurement error, strange comet, or an alien probe that just executed a tactical adjustment right under humanity's nose. The data is real, the evidence undeniable, but the truth is still hurtling through the darkness at 70 km/s. Do you dare face what's coming toward us? Like and subscribe now, so you don't miss a thing, where we tear apart every pixel of data and confront the most terrifying possibility. In 2025, in October, the universe revealed a secret. On the 29th, the alien visitor named 3I Atlas skimmed the area near the Sun. This is a familiar flyby for many celestial bodies, but the results completely challenge the existing laws of physics. Monitoring data from observation stations recorded a sudden acceleration. It did something that a drifting rock mass is never allowed to do. This acceleration came with no visual signs. No escaping gas trail, no clear smoke plume. The object shifted its actual position compared to the predicted position on the orbit, a 4 arcsecond deviation. This tiny shift proved that some force had acted on it. The force was not gravity, a thrust with no confirmed physical origin. The only thing that appeared was a strange blue light standing out in an area that should be flooded with the red light of dust. Scientist Avi calculated the parameters and discovered that the required thrust was extraordinary. If it wasn't catastrophic mass release, then there needed to be an energy source or deliberate intervention. Subsequent orbital analyses by scientists painted a worrying picture. If this acceleration continues, the object's orbit will lead it to a perfect alignment with Earth. The object will intersect our orbital plane. This tiny adjustment at the point near the Sun could be a random coincidence, or it could be a calculated course correction, a deliberate action. At the same time, important images of Mars were also missing. Data about the interstellar object and the neighboring planet disappeared in the same time frame, making this mystery even deeper. This suggests a completely different possibility. The object that flew by might not be a stray comet. We may have just witnessed something intelligent performing a flight adjustment in our solar system. What we see is data. The data is real. The measurements are real. This forces us to reconsider every assumption about extraterrestrial life and technology. While everything on Earth continues as normal behind the Sun, an event occurred that shouldn't exist. The object 3I Atlas, already unusual with its interstellar origin, performed a move that challenges the laws of physics. It changed direction. The change wasn't sudden, but it could be measured with sophisticated instruments. In the space environment where every motion is governed by gravity and can be predicted with precise equations, any deviation carries great significance. This object, named after Hawaii's search system, is the third confirmed interstellar visitor. It traveled through the space between stars, and now it is approaching the Sun at Perihelion. This most dramatic moment was obscured from ground-based telescopes. Only spacecraft designed to observe the Sun could see it. It was these spacecraft that recorded evidence of the extraordinary event. Scientists at NASA's Jet Propulsion Laboratory compared the actual orbit with the orbit predicted based solely on gravity. The result was a significant difference. This deviation was about 4 arcseconds. The number 4 arcseconds sounds small. That angle is just a tiny fraction of a degree. But at distances of millions of kilometers and speeds of tens of kilometers per second, this deviation means the object veered hundreds of kilometers from its expected orbit. It did this in just a short period of time. Data overlaid from Soho Stereo and GOES 19 all tell the same story. When aligned and the expected position is subtracted, the residual that is the difference between reality and prediction consistently appears as 4 arcseconds across all instruments. This is not random noise. This is a unified signal. Avi immediately grasped the significance. He is the one who has spent years proving that Oumuamua, the first interstellar visitor, could be an artificial object. He recalculated and confirmed that to change the orbit that much a large thrust is needed. This thrust needs a significant momentum transfer. If that thrust came from comet gas escape, then a huge amount of material would have to be ejected. According to his calculations, 3I Atlas would have to lose about 1/16 to 1/10 of its total mass to create this acceleration. A mountain would have to lose a significant portion of its mass in just one pass by the sun. The lost material would have to turn into gas and dust, creating a huge and bright cloud. This should have been captured by every telescope pointed in that direction. But this is where the story turns strange. The object did brighten as expected from a comet sublimating near the sun. However, the color was completely wrong. Instead of turning red like comet dust usually does when scattering sunlight, 3I Atlas turned blue. In some measurements, this blue was even bluer than the sun. Blue light indicates shorter wavelengths, finer particles, or ionized gas. This proves that something unusual is scattering or emitting this light. Normal comets cannot produce this color and signature, so we have an object accelerating beyond gravitational limits, a brightening confirming activity, but no huge gas cloud or clear jets. Plus a color change that doesn't match normal comet gas escape. Each piece of evidence seems to contradict the others. This event is not simple. The cumulative effect of that acceleration began to be considered. If the deviation is a real velocity change, though small, it will accumulate. Space is very vast, and orbits are very sensitive. A small velocity change over many weeks can create a large total delta V. This can change the shape of the orbit, altering the object's approach distance to Earth. The expected encounter in December 2025 will no longer follow the original orbit, so the question remains and is very urgent. Is this just asymmetric comet gas escape, or a glitch in the measurement data, or something completely different, something deliberate? A flight adjustment. This orbit control is from a spacecraft, not a comet. Determining the position of a fast-moving object near the sun from spacecraft millions of kilometers away is not simple. It is a multi-stage process, and each stage can cause errors. These errors can accumulate and amplify, turning a real signal into noise, or worse, noise into a false signal. We need to understand why the 4 arcsecond acceleration is believed. The process starts from raw images. Spacecraft like SOHO and Stereo are not designed to track small objects. They are solar observatories. Their cameras are optimized for the corona. They use coronagraphs to block the sun's bright disk. However, comets and asteroids sometimes enter the field of view, appearing as moving bright spots. 3I Atlas was one of them. Those frames became data, but raw images are very complex. The object can be saturated sunlight scattering, creates glare bands across the entire image. Cosmic rays create bright streaks. The first step is to clean the data, stack multiple images, align them by background stars, and subtract the average to remove fixed features. What remains are temporary light sources, objects that have moved. Next is to determine the center. The exact position of the object in the frame needs to be found. This requires applying a mathematical model to the bright spot the object creates. If the object is saturated or has a coma, its center can shift. Even a small part of a pixel can translate into arc seconds in the sky. Once the center point is obtained, a reference point is needed. Background stars are cross-referenced with an accurate catalog such as Gaia to determine sky coordinates. This process assumes the spacecraft knows exactly where it is pointing. If the orientation is slightly off, or the timing is inaccurate, the entire reference system will shift. Then the measured position is compared to the predicted position. The predicted position comes from an orbit model based only on gravity. JPL calculates temporary positions for every known body in the solar system. When they compared that prediction with actual measurements from the spacecraft, the 4 arcsecond difference appeared. The object did not obey the laws. But the problem is here. Every step in this chain can cause errors. Saturation can distort the center point. Catalog mismatches can propagate into false deviations. The sun's brightness makes all these effects worse. Photometry near the sun is one of the most difficult types of photometry. So how much should we trust that 4 arcsecond number typical comet measurement accuracy far from the Sun can reach under a quarter arcsecond? Near the Sun, accuracy decreases. Systematic errors of 1 or 2 arcseconds are reasonable. If the error is 2 arcseconds, the entire signal is halved. If there is a 3 arcsecond deviation, then the actual signal is very small. The question is whether the data processing teams accounted for all systematic errors. Is there a hidden residual error in the measurement that we are confusing with the real physical effect? The only way to know is to reprocess the data independently. Need to take the raw frames, not the processed catalogs. Run a separate center determination algorithm. Use a different star catalog. Compare results from different instruments to see if they match. Check time dependence. Real acceleration must create a time-dependent signature, a clear curve. So far, the public has not seen a completely independent analysis. We are relying on claims and preliminary results. This does not mean they are wrong, but it means they are not completely certain yet. Doubt is very important. If the measurement fails, if the 4 arcseconds are a system error, the whole story collapses. The necessary mass loss will decrease. The color anomaly may still be strange, but the urgency will disappear. Speculation about artificial thrust becomes unnecessary. But if the measurement is still correct, if independent analyses confirm the 4 arcsecond deviation, we must explain it. This is when everything becomes interesting. Conventional explanations begin to strain. When an object changes, velocity momentum must be conserved. Newton's third law is very clear. If 3I Atlas accelerated, something was pushed in the opposite direction. This requires ejecting mass. AVI did this calculation. He calculated backward from the observed acceleration to the ejected mass. Those numbers are not reasonable. The concept is very simple. Momentum is mass times velocity. If you want to change momentum, you must eject mass with a certain velocity. Rockets do this by burning fuel. Comets do this by sublimating gas. Sublimated gas will carry momentum. If the gas escapes asymmetrically, it will create thrust. Low put the numbers into the formula. The acceleration implied by the 4 arcsecond deviation requires a certain amount of momentum. Assuming the ejected material has typical comet velocity about 1 km per second, the necessary mass to eject is from 1/16 to 1/10 of the object's total mass. This is a catastrophic material loss. A loss that should have created a huge cloud of dust and gas easily visible from afar. But the paradox is here. Where is that cloud? A comet losing 1/10 of its mass does not happen quietly. They create spectacular displays. Gas streams erupt from active regions. Dust is swept along and scatters sunlight, making the coma bright. Sometimes the nucleus fragments. 3I Atlas did brighten, but the reports do not describe the type of massive gas escape event that you would expect when losing a large part of the nucleus. There was brightening, there was a strange blue color, but where is the dense gas cloud? Where are the jets? Where are the spectral signs of huge gas release? Let's consider the alternatives. Perhaps the ejection velocity is much higher than usual. If the gas is ejected at a few kilometers per second, instead of 1, you will need less mass. But how to do that? Comet sublimation does not create those velocities. It would require an explosion, a rapid energy release. Or perhaps the mass loss was extremely well dispersed. A narrow jet to the point that it carries all the momentum in one direction but does not spread into a visible smoke cloud. This is theoretically possible but requires a very specific vent shape. Gas expands. It diffuses. Another possibility is that the ejected mass is not gas at all. What if it is solid matter, rocks or ice ejected at high velocity by some internal process? Solid ejected matter does not scatter sunlight like gas. It may be harder to detect, but even this scenario is very strange. Comets do not automatically eject kilograms of solid mass in directed streams, so the paradox remains. Acceleration shows large mass loss. Brightening shows something is happening, but the visible signs do not match the scale of mass loss needed. Either our acceleration measurement is wrong, and the mass lost is much smaller, or the mass loss occurs in a way that does not fit normal comet behavior. Or there's a third option. What if the acceleration does not come from mass ejection? if it comes from a mechanism that does not require ejecting 1/6 of the object's mass. An efficient, deliberate, and controlled mechanism. This is when the conversation turns to grounded speculation. If the acceleration cannot be explained by natural gas, escape without invoking astonishing mass loss, astonishing column stratification, or astonishing ejection velocity, then alternative mechanisms must be sought. Solar sails, photon pressure, thermal decomposition from direct sunlight. These technologies, and once you consider technology, you are considering the possibility that 3I Atlas is not natural at all. Color in space is an important clue. It tells you about composition, about temperature, and about the size of the particles scattering light. The color of comets tells what kind of dust and gas is being released as it heats up. The fact that 3I Atlas turned blue near Perihelion is not just unusual, it is a serious anomaly. Typical comets usually do not turn blue when they approach the sun. Dust particles ejected from the nucleus scatter sunlight, and scattering depends on particle size. Particles larger than the wavelength of light tend to scatter toward longer wavelengths toward red. Comet dust clouds work similarly. As a comet heats up, you predict it will turn redder. But 3I Atlas turned blue. The color index shifted toward shorter wavelengths, bluer than the sun in some observations. This is contrary to what normal dust should do. So what creates blue light in comets? One possibility is ionized gas. When high-energy ultraviolet light from the sun hits gas molecules, it can ionize them. These ions then emit light at specific wavelengths, often blue or green. Ionized carbon monoxide gas is one of the main candidates for blue in comets. However, the amount of ionized gas needed to create this dominant blue light is very large. Comets usually have a greenish shell around the nucleus, but the brightness is not enough to overcome the brightness of dust. If blue light is dominant, that means dust has disappeared, or ionized gas is being produced at an inexplicable rate. The second possibility is very small particles. Dust particles smaller than the wavelength of light can scatter blue light more efficiently, an effect called Rayleigh scattering, or me-scattering. If 3I Atlas somehow only released very fine dust particles in its gas escape process, it could turn blue. But this again contradicts the absence of a visible gas trail. Fine dust particles are also easily pushed by solar radiation pressure, creating a clear dust tail. That tail did not appear. The particle size needed to create blue would require a very selective and unusual gas escape process. The third possibility is a reflective surface. If the object's surface is made of a material that can reflect blue light better than other wavelengths, such as water ice that has undergone some processing or another type of material, then it could create blue light when passing the sun. But why would the surface change reflectivity at perihelion? Heating evaporates ice, not makes it glow blue. Any reflective surface would have to face temperature and radiation pressure challenges. This blue color is a headache. It is not just a color. It is a diagnostic sign for something very different. It suggests an absence of coarse dust, a dominance of ionized gas, or a completely different material composition. If it is gas, then where is it? If it is fine dust, why does it not create a clear tail? The combination of acceleration without visible thrust and strange blue light is a toxic combination for conventional explanations. It pushes us out of the range of known comet physics. 3I Atlas is not just doing something unusual, it is doing it in a way that contradicts what we think must happen. In addition to physical and optical anomalies, this event also causes orbital concern. The original orbit of 3I Atlas was calculated. It is a passing object, not a colliding object, but the velocity change at perihelion changed the outcome. The 4 arcsecond deviation, a small initial velocity change, accumulated in space and time. As it left the sun, its new orbit was shaped. Scientists recalculated and found that this new orbit leads it to an almost perfect alignment with Earth. In December 2025, is this alignment a random coincidence? Earth moves in its orbit, the interstellar object does too. 2 orbits intersecting at a specific point can happen, but when an unnatural velocity adjustment occurs right before this event, randomness becomes suspicious. If this acceleration is a deliberate action, then it could be an adjustment to achieve this intersection position. A small control maneuver performed at perihelion, where the sun's gravitational energy can be used to achieve maximum effect with minimal energy cost. This type of control is called adjusted gravity assist. It is performed by our spacecraft, but it requires intent and the ability to create precise thrust. A comet has no intent. It only reacts to heat. Calculating an Earth-intersecting orbit and adjusting velocity to achieve it is a complex maneuver. If 3I Atlas is a probe, then this event would be a tactical maneuver. It would be a way to achieve the closest possible flyby, an opportunity to observe Earth. At the same time, there are reports of lost Mars image data. In the same time frame, telescopes observing Mars experienced unexplained malfunctions. Images were not recorded. This coincidence makes the suspicion of deliberate acceleration even clearer. Could this be a jamming event, an action to conceal another event? If 3I Atlas is a probe, then approaching Earth could be the goal, and the loss of Mars data could be a shielding maneuver, an effort to avoid observation during orbit adjustment. No explanation is simple. Both the acceleration and the alignment pose questions that cannot be answered with known comet physics. They force us to consider the possibility of extraterrestrial technology and intelligence. 3I Atlas is not a normal drifting ice and rock. The data is clear: the object accelerated without visible gas, escape it emitted unusual blue light, and its new orbit leads it to a close intersection with Earth. These three anomalies together form a paradox that cannot be explained by conventional astrophysics. Either all our measurements are systematically wrong, or we are witnessing a deliberate action. An orbit control. A flight adjustment. If it is a comet, then it is a comet that defies every rule. However, if it is a spacecraft, then all the data makes sense. High-efficiency acceleration without ejecting large mass. Blue could be light from an ion engine or some propulsion system. The orbital alignment is the goal of a probe flight. We do not yet have a final answer. No one does. But the data has been measured. The deviation has been confirmed. We are standing on the threshold of a major discovery. The next part of this story will be monitoring the Earth flyby. That is the last chance for telescopes to resolve this mystery. We need to look for signs in asymmetric shape, a heat emission pattern, or an accompanying object. The 3I Atlas event is a reminder that we do not know everything. The universe still has many mysteries. And sometimes the simplest answer is the most extraordinary one. We need to continue observing and be ready to accept the impossible. These ions emit light at specific wavelengths when electrons recombine or transition between energy levels. For example, carbon monoxide ions emit blue and ultraviolet light. Nitrogen ions do the same. If an ionized gas cloud dominates rather than dust, you'd see blue emission. This can absolutely happen in a cometary environment, though it's usually not the dominant color signature. Second, fluorescence. Some molecules, when excited by sunlight, re-emit that energy at characteristic wavelengths, a process called fluorescence. Carbon monoxide and carbon dioxide can produce blue-shifted emission. Cyanogen, another common comet molecule, emits strongly in violet blue. If 3I Atlas has an unusually high content of these molecules, the blue could be a natural phenomenon. But that raises questions about composition. Why does this object have more carbon monoxide or cyanide than water ice, which dominates most comets? Third, ultrafine dust. If the dust grains are extremely small, smaller than the wavelength of visible light, they preferentially scatter blue light through a process called scattering. This is the same effect that makes Earth's sky blue, where tiny atmospheric molecules scatter short wavelengths more than long ones. So the sky looks blue. If 3I Atlas released a nanodust cloud, it could appear blue. But producing dust that fine requires something unusual. Typical comet dust is micron-sized or larger. To get down to tens of nanometers, you'd need special minerals that fragment into tiny pieces, or some process grinding material into ultrafine grains. That doesn't happen naturally. Then there are even stranger possibilities. What if the blue comes from a metallic surface? If the nucleus or part of it is reflective metal, it could scatter sunlight in unexpected ways. Nickel, for example, has a slightly blue reflection spectrum. And here's where it gets exciting. Preliminary spectroscopy of 3I Atlas reportedly showed high nickel emission. Nickel isn't common in comets. It's a metal usually locked in rocky or metallic grains deep inside primitive bodies. Seeing nickel emission suggests either an unusually metal-rich cometary nucleus or something exposing or vaporizing metallic material. Another weird possibility, active illumination. Sounds crazy, but bear with me. What if the object isn't just passively scattering sunlight but actively emitting blue light? Not fluorescence, but real powered emission, a glowing surface, possibly from heat, or possibly from an internal energy source. That would be extremely unusual for a natural body, but perfectly feasible for an artificial one. A spacecraft could have reflective coatings, could use ablative materials that glow when heated, could even have lights or devices emitting in the blue. Again, pure speculation, but the blue isn't easily dismissed. Spectroscopy adds layers. If we had high-resolution spectra showing strong emission lines from carbon monoxide or cyanogen ions, we could comfortably say the blue is from gas. If we saw a smooth continuum with no strong lines, just a blue slope that points to fine dust or reflective scattering. And if we saw atomic emission lines from metals like nickel or iron, that's a red flag, not figuratively red, but a warning something abnormal is happening. Metals don't usually vaporize in cometary environments. They require high temperatures, violent processes, or compositions we don't normally associate with icy bodies from the outer solar system or interstellar space. The combination of blue color, brightening, and acceleration all blend into a puzzle where no piece quite fits. If the object ejected a huge amount of gas to produce the acceleration, we'd expect to see that gas, and it would dominate the color signature. If it ejected fine dust, we'd see blue. But fine dust doesn't produce much thrust. If it has a metallic surface or vaporizing metal, that's bizarre, but could explain both the color and potential alternative thrust mechanisms like thermal destruction or photon pressure. Each explanation works for part of the data but fails on another, and that's when the investigation starts to feel less like solving a problem and more like facing a phenomenon with no clear answer. The standard tools, the standard models, they get you part of the way, but they leave gaps. They leave questions. And those questions fuel speculation, social media threads, accusations, and excitement. Because when the data doesn't fit the models, people start proposing new ones, some reasonable, some wild. And one of those wild proposals, the idea that the geometry of the December flyby might have been intentionally altered, comes from a simple calculation of accumulated velocity. That story, and how it spread, is what we'll dig into next. Once the anomalies, the acceleration, the blue color, the brightening became public knowledge, they didn't stay confined to academia. They leaked, or rather they exploded across social media forums, threads where amateur analysts and space enthusiasts dissected every scrap of data they could find. And communities using public orbital tools and software started running their own calculations. One of those calculations went viral. It was the 50-day delta V scenario. The logic was simple. If 3I Atlas underwent a small but continuous acceleration during and after perihelion, that acceleration would build up over time. Even a tiny force applied constantly adds up, so someone ran the numbers. They assumed the 4 arc-second deviation represented a real acceleration on the order of a few millimeters per second squared. Then they integrated that acceleration over 50 days from late October to mid-December before the Earth flyby. The result, an accumulated velocity change of about 86 meters per second or delta V. 86 ms isn't huge in space. It's a modest energy expenditure for a spacecraft, but enough to significantly alter an orbit. Over tens of millions of kilometers, an 86 ms velocity change translates to a positional difference of tens of thousands of kilometers by the time you reach your next target. And the next target in this case is Earth. The December 2025 flyby, originally predicted as a distant past, suddenly looked different if you factored in the delta V. This is where the Earth alignment story began. Analysts started redrawing the adjusted orbit, showing the object's path could shift closer to Earth, possibly aligning more directly with our planet's position in December. Some even claimed the geometry could bring it within a few Earth radii, not just a flyby, but a close encounter. The implication was unmistakable. If the acceleration is real, if the delta V accumulates, the object might be self-aligning. And alignment suggests intent. Intent suggests intelligence. Intelligence suggests something far more provocative than a comet. Now, before diving deeper, let's be clear what this is. This is social analysis. This is community speculation, often done by people with real orbital mechanics skills, but without access to the full data set, without peer review. and without the institutional checks mainstream science uses to filter noise from signal. The 50-day delta V calculation assumes constant acceleration, no damping, no measurement error. It assumes the 4 arcseconds are fully real and fully due to thrust. If any of those assumptions are wrong, the calculation fails. And as we discussed in Part 2, there are plenty of reasons to doubt whether the 4 arcsecond deviation is fully real. But ignoring the assumptions the calculation spread, it became a talking point. Videos, blog posts, forum threads all ran the numbers and reached the same conclusion. 86 ms Earth alignment December, and once that story took off it had a life of its own, because humans are pattern-seeking creatures. We see intent where there might be none. We connect dots that might be random, and when dark spots appear in space when they involve an object from outside the solar system, when they coincide with claims of acceleration and odd colors, it's almost impossible not to wonder. Then the missing Mars images surfaced. Someone noticed while scrolling through mission data archives and timelines that images from Mars orbiters during the same period seemed delayed or unreleased. The high-resolution imaging science experiment regularly photographs the Martian surface and occasionally catches flyby objects, but certain frames from late October or early November weren't published. Other instruments seem to have gaps too, not necessarily unusual. Mars missions have downlink schedules, data priorities. Sometimes instruments go into safe mode, or aren't pointed where you'd expect, but the timing was suspicious. Right around perihelion, right when 3i Atlas was most active, the conspiracy-minded whispered, "Why are Mars images missing unless they show something the authorities don't want the public to see?" What if a Mars orbiter caught 3i Atlas, at perihelion saw the acceleration, saw something artificial, and the data got buried? This is how information gaps fuel speculation. When data is missing, when explanations aren't offered, people fill the void with narratives. And the narrative around the missing Mars frames became deliberate cover-up. Let's look at the mundane reasons data gets delayed or lost, because they're boring but critical. Spacecraft orbiting Mars operate on tight schedules. Data is downlinked in batches, often prioritizing surface imaging over opportunistic targets. Instruments have pointing constraints. You can't always swivel to catch a comet flyby if you're scheduled to image a future landing site. Spacecraft also weather anomalies and instruments temporarily shut down for self-preservation. Solar conjunction periods when Mars is near the Sun from Earth's view restrict communication windows. All of this happens routinely. Nothing requires a conspiracy, but transparency matters. If the agencies running Mars missions simply issued a statement explaining why certain frames were delayed or confirmed no observations of 3i Atlas were made, the speculation would evaporate. Instead, there was silence, or at least perceived silence, which in the age of social media is nearly as bad as actual silence. Lack of information becomes evidence of suppression in the minds of pattern seekers, and fair or not, it shapes the narrative. So now we have layers, technical anomalies, acceleration, the color puzzle, the mass loss paradox, and layered on top of all that, a social story involving delta V calculations, Earth alignment, and missing data. Each layer reinforces the others. The acceleration makes the missing images matter. The missing images make the alignment claim seem plausible. And the whole story leads to a narrative that 3i Atlas isn't just a weird comet, but something far more alien, something worth scrutinizing, doubting, even fearing or thrilling over, depending on your perspective. But scrutiny demands data. It demands testing hypotheses, stress testing models, comparing predictions to observations, and that's what we'll do next. In Part 2 of this investigation, we'll go through each competing hypothesis one by one. We'll stress test the outgassing model, examine the artifact hypothesis, and yes, we'll even explore the possibility of technosignatures. Not because it's likely, but because if the natural explanations don't hold up, we have to consider what's left, and what's left might be the most fascinating question of all. The default explanation for any non-gravitational acceleration in a comet is outgassing. It's the first hypothesis any astronomer reaches for, and for good reason. Comets outgas. It's what they do. So before entertaining exotic alternatives, we need to test whether outgassing can actually explain everything we see with 3i Atlas. Not just hand-waving, Not just saying outgassing happens, but actually running the numbers, checking the geometry, seeing if the model holds up under pressure and stress testing it. Outgassing occurs when solar heat warms the nucleus, causing it to sublimate directly from solid to gas. Water ice is the dominant volatile in most comets, but carbon monoxide, carbon dioxide, methane, and other molecules also contribute to sublimation. As the gas expands away from the surface, it carries momentum. If the outflow is isotropic symmetric in all directions, the momentum cancels out, and there's no net force. But if the outflow is anisotropic, stronger on one side than the other, you get thrust. The cometary nucleus acts like a tiny uncontrolled rocket. This is well documented. Many comets show small orbital perturbations due to non-gravitational forces from outgassing, but the key word here is small. Typical cometary non-gravitational accelerations are on the order of 10 ounces, 7 LLs, or 10 Ls, 6 LLs, ms2. If the 4 arcsecond deviation is a real acceleration near 10 sound, 4 bar, or 10 sound, 5 ms2. That's orders of magnitude larger, not impossible, but at the extreme upper end of what normal outgassing produces. So the first question is, can sublimation produce thrust that large? The answer depends on mass loss rate and exhaust velocity. If you sublimate 1 kilos of gas per second at 1 kilometers s, you generate 1 N of thrust. For a small nucleus, say, 100 meters in diameter with a mass of a few million kilobol, 1 N produces an acceleration of about 10 centimeters, 4 to that's S2. That matches the required magnitude, but now you need to sustain that acceleration for hours or days. 1 kilojoules as over 1 day is 86, that's 400 kilojoules. Over 10 days, that's 864,000 kilojoules. That's a significant fraction of the nucleus, if the total mass is only a few million kilojoules. We're back to the mass loss paradox, so maybe the exhaust velocity is higher. Carbon monoxide is lighter than water, so it achieves higher thermal velocities. At perihelion temperatures, maybe you hit 2 kilometers. That halves the required mass loss rate. Now you're losing half a kilo instead of a full kilo. Over 10 days, that's 432,000 kilojoules. Still significant, but more plausible. Except now you have to explain why the cloud looks relatively faint. 432,000 kilos of carbon monoxide released over these days would produce a visible cloud. It would scatter sunlight, show up in images, produce strong emission lines in spectra. And while 3i Atlas did bright in reports don't describe the dense massive coma you'd expect from that scale of mass loss. Then there's the geometry issue. For outgassing to produce thrust, the outflow must be highly anisotropic. You need jets active regions on the surface where gas escapes preferentially. Comets do have jets. Spacecraft images of comet nuclei like Rosetta's show jets erupting from specific locations. Those jets produce force vectors that can be calculated if you know their direction and intensity. But to produce the observed acceleration in 3i Atlas, the jets would need to be precisely aligned. The thrust vector would have to be in the direction that produces the 4 arcsecond deviation. Let's break down the required vector. The deviation was observed near perihelion when the object was behind the Sun from Earth's perspective. That means the displacement could be radial, pushing the object away from or toward the Sun, or transverse perpendicular to the object's sun line. Radial acceleration from solar heating is expected. Gas sublimates more on the sunward side, pushing the nucleus outward, but radial acceleration doesn't explain transverse displacement. To do that, you need jets oriented transversely perpendicular to the sunward direction, and those jets would have to dominate over the radial component. This is where the model gets specific and testable. If we had high-resolution images of the nucleus, we could look for active regions. We could map the jets, calculate their directions, estimate gas output from each region, and predict the net thrust vector. Without those images, we're just guessing. We can say there might be a jet on the western limb pointing backward, but we can't verify it. The model becomes unfalsifiable, and that's a problem. Science demands testability. If every anomaly can be explained by invoking an invisible jet in just the right place, the explanation loses predictive power. There are also thermal limits. The cometary nucleus absorbs sunlight, converts it to heat, and that heat drives sublimation. The amount of gas you can produce is limited by energy input. At 3I Atlas's perihelion, it was close to the Sun, so energy input was high. Still, there's a maximum sublimation rate based on surface area and composition. Water ice sublimates at a certain rate per m2 per second at a given temperature. Carbon monoxide sublimates faster but also requires more energy to heat the nucleus initially. If the nucleus is insulated by a dust mantle, sublimation may only occur in specific regions where the mantle is thin or absent. Thermal models are complex, but they constrain what's possible. Some researchers suggest 3I Atlas might have had a subsurface outburst. A pocket of volatile material heated gradually over weeks or months suddenly vents when pressure exceeds a critical point. This could produce a strong sudden jet generating large thrust in a short time. Outbursts have been observed in other comets. They explain sudden brightening, temporary coma expansion, sometimes even nucleus fragmentation, but they're rare and unpredictable. Invoking an outburst is convenient, but also a bit of a cheat. Any anomaly can be explained by an outburst if you're willing to say something unusual happened. We can't see it. Let's also consider the blue color in the context of outgassing. If the acceleration comes from carbon monoxide or carbon dioxide outgassing, that gas would be ionized by solar UV, and the ions would emit blue. That's absolutely true. The blue supports the gas hypothesis. Except the mass loss paradox remains. You need a lot of gas to produce the thrust, and that much gas would produce a long-lasting bright coma. The color might fit, but the brightness and overall morphology might not. Another angle: fine dust entrained in the gas flow. If the nucleus is dusty gas, escaping the surface drags dust grains with it. Fine dust, as we discussed, scatters blue light. If the dust-to-gas ratio is high, and the dust is very fine, you get blue scattering, and potentially brighter appearance per unit mass. However, fine dust also reduces thrust efficiency. The gas has to accelerate the dust, which takes energy and momentum. The more dust, the less thrust you get for a given mass loss rate. You can't have it both ways. You can't simultaneously explain the blue with fine dust and the acceleration with efficient gas thrust. So where does the stress test leave us? Outgassing is still a plausible mechanism, but it requires a specific, somewhat contrived combination of circumstances. High mass loss rate, highly anisotropic outflow, unusual composition favoring carbon monoxide or other volatiles, fine dust to explain the color, and all of this happening without producing the massive gas envelope we'd expect. It's not impossible. Nature loves surprises. But the model is being stretched. It's working hard to fit the data, and when a model has to work that hard, when you have to invoke multiple special conditions to make it fit, that's a signal. The model might still be right, or there might be another explanation waiting. But before we get there, we need to consider one more natural possibility. What if the measurement is wrong? What if this is all an artifact? Every extraordinary claim in astronomy has to pass the artifact filter. Before announcing a discovery, before publishing a paper, before speculating on implications, you have to rule out the possibility that what you're seeing is just a ghost in the machine, an instrument glitch, a processing error, a systematic bias mimicking a real signal. This isn't skepticism for its own sake. It's a necessary discipline because the history of astronomy is littered with false alarm signals that turned out to be noise discoveries that crumbled under scrutiny. So let's scrutinize. Let's ask whether the 4 arc-second deviation might be an artifact. Let's start with saturation. When a sensor pixel gets too many photons, it overflows. Charge spills into neighboring pixels, creating blooming or streaking features. The centroid, the calculated center of the light distribution, shifts. Now, 3I Atlas was observed in coronagraph images near the Sun. Bright background. Scattered sunlight floods the detectors. Even with the Sun blocked by a coronagraph mask, the corona is still blazing. If the object is bright enough to saturate, or if the background gradient is steep, the centroid can skew, shifting systematically in one direction. Shifts from arc-second level to sub-arc-second are totally possible. If you have a 1 arc-second offset and don't correct it, you've already explained a quarter of the observed deviation. If multiple frames have slightly different saturation levels due to changing object brightness or background, the offset can vary, creating a murky, time-dependent signal. This is subtle. It requires careful modeling of detector response. And if that modeling isn't done or is done wrong, the artifact persists. Next, spacecraft pointing. SOHO and stereo know their positions through a mix of star trackers, gyroscopes, and ground-based ranging. But position knowledge still has uncertainty. As SOHO has sub-arc-second uncertainty in normal ops but bigger near the sun, where star trackers may have fewer stars, or where thermal bending affects instrument alignment. If the pointing reconstruction is off by an arc-second, and that error isn't random but systematic in one direction due to observation geometry, it propagates into the object's measured position. You think the object moved, but really the spacecraft's estimated pointing shifted. Timestamping is another culprit. Every image has a timestamp the moment the shutter opens or exposure begins. That timestamp needs to be accurate to milliseconds or better for precise astrometry. If the spacecraft clock drifts or the timestamp is assigned wrong in data processing, the object's position gets mapped to the wrong moment. When compared to predicted ephemerides calculated for specific times, timing error looks like position error. A few seconds of timing error at cometary speeds can cause arc-second level position shifts. Next, reference frame. Astrometry requires matching background stars to a catalog. Gaia might be the gold standard, pinning billions of stars with unmatched precision, but try doing that right next to the sun. Nearly impossible. The background sky fades into glare. The coronagraph trying to block the sun also wipes out most of the surrounding sky. You're lucky to have a few reference stars left, but they're often too bright, fully saturated, or drowned in scattered light noise. When your reference stars are skewed, or worse, the star catalog you're using has inherent systematic errors. The whole calculation collapses. The transformation from detector coordinates to sky gets warped. And that error, it doesn't vanish. It gets baked straight into the final object position. And that's just the first layer of error. To see through the noise, astronomers stack series of images aligning them by fixed stars. But we're tracking a moving object. You have to calculate rotate frames to follow it. If your motion model is off even slightly, the object in the final stack smears. The center of that smear is no longer the true position. You just created an artificial offset yourself. Worse if the stack spans hours, even days. The object's motion has changed. What looks like a real acceleration could just be a ghost in the data processing. This is where you need an error budget, a standard sanity check. Try this list every error source. 5 arc seconds from saturation, 3 from timing, 2 from reference frame, 4 from stacking algorithm. Add them statistically, you get a random error of about 8 arc seconds. But that's the best case. If the errors are systematic, if they don't cancel, but add up 5 plus 3 plus 4, you get 12 arc seconds of bias. That's already 30% of the signal. If they all point the same way, the error can reach 2, even 3 arc seconds. That alone explains half the observed deviation. The million-dollar question: did the data processing team actually check all this? Did they simulate saturated point sources to see how far the centroid shifts? Did they cross-check multiple reference star catalogs? Did they try different stacking algorithms? These are basic validation steps, but they're incredibly time-consuming. And when observations are released almost in real time, when public pressure is counting down to the December flyby, is it possible? A few steps got skipped. We can't know for sure because the detailed methodology is still in the dark. All we have is a number 4. Arc seconds. We have excitement, and we have endless speculation. What we don't have is a detailed error analysis. No diagnostic plots, no pipeline comparisons. Those might come or they'll get buried as the story fades, or if the December observations show nothing new. This is the ugly face of science and progress. You're forced to act on incomplete information. But let's set skepticism aside. Assume they checked everything. Assume the deviation is real. Assume other independent analyses confirm it. We still need an explanation. And if all natural outgassing models fail, if the mass loss and color paradoxes remain, then we're left with only one possibility, the most controversial one, the one still lurking in the shadows, the one that excites Avi Loeb and makes the rest of the scientific community frown. What if 3i Atlas isn't natural? What if it's technology? Let's explore that hypothesis, not as dreamers but as investigators. What would a techno-signature look like? The idea isn't new. Oumuamua, the first interstellar visitor in 2017, sparked the exact same debate: weird cigar-shaped, mysterious acceleration as it left, and the total absence of any coma or dust tail. Avi Loeb publicly proposed Oumuamua might be a light sail, a thin sheet pushed by radiation pressure itself. A bombshell idea. It was heavily criticized but couldn't be fully ruled out, because the data didn't fit perfectly with any natural explanation. And in science, when nature dead ends, you're obligated to consider alternatives, even the strangest ones. So what traces would an artificial object passing through the solar system leave? Let's look at technologies that could explain the 3 Atlas observations. First, low-thrust ion engine. Think electric propulsion, continuously accelerating ions and shooting them out the back at insane speeds. Thrust is tiny, just a few millinewtons, but it runs continuously for long periods, building up significant acceleration. A ship using an ion engine could absolutely produce the acceleration we see. Power required, just a few kilowatts. Totally reasonable for a spacecraft with solar panels or a mini reactor. But here's the fatal flaw. Ion engines aren't invisible. They spew a plasma plume, a glowing stream of ionized gas, across the spectrum. It would be visible. Spectroscopists would have picked up weird emission lines. No reports show that. This doesn't rule it out completely. The plume could be too faint, or it's pointing straight away from us, but it's a missing piece. If you want to bet on the ion engine hypothesis, you have to answer, where's the exhaust? Second hypothesis, a photon sail. This is passive tech. No exhaust. No fuel. Just a giant reflective surface catching sunlight. The momentum from photons hitting and bouncing off pushes the sail. The force is extremely weak. At Earth's distance, it's 9 newtons per square kilometer of surface. But as 3i Atlas raced toward the sun at perihelion, that force spikes hundreds of times stronger. A sail with an extremely high area-to-mass ratio, say 100 megatonnes, would feel a massive acceleration kick. And here's the key. A giant reflective sail flying close to the sun. It would light up like a beacon. Exactly, it would be blindingly bright. A photon sail is essentially a mirror. Depending on angle and surface structure, it could absolutely be engineered to preferentially reflect blue light, explaining the weird color. This hypothesis also perfectly explains the lack of a coma because there's no gas, just pure reflected light. The acceleration would be radially outward from the sun unless the sail is designed to tilt or curve, a complex but totally feasible navigation technique to alter the thrust vector. But the photon sail hypothesis has a fatal flaw. It requires an unrealistic area-to-mass ratio. Oumuamua's acceleration demanded a sail thinner than a millimeter. With Atlas, we're talking a spider silk-thin structure spread over a massive area, somehow surviving thousands of years of interstellar travel. Dust impacts micrometeoroids, only to plunge into the hellish heat of perihelion. That sail would heat to thousands of degrees. It would have to be made of a miracle material. Graphene. Or something our tech doesn't even know yet, hard to swallow. Third option, thermal ablation. Use directed energy, maybe a laser or focused sunlight, to vaporize the object's own surface. The vaporized material, whether rock or ice, creates thrust. Basically, it eats itself to move. The vapor plume could look a lot like cometary outgassing. The difference is in the details: vapor composition, exact temperature, and the blue possible if the ablating material is metal-rich or ionized. Of course, any active propulsion needs energy. At perihelion, solar panels would be flooded with power, or more efficiently, a compact nuclear reactor. We've sent spacecraft with nuclear power. An advanced civilization certainly could. Energy isn't the barrier. So if it's artificial, what should we look for first? Deliberate acceleration. Cometary outgassing is chaotic and random. Engine thrust is steady, controllable. We could look for patterns. Does the thrust turn on and off? Does it vary cyclically? Any structure in the acceleration profile is a huge clue. Second, unnatural spectral signatures. Exotic metals, rare elements. The nickel hint is a red flag. Nickel is construction material not common in icy comets. Seeing nickel vapor suggests a metallic structure being heated to vaporization. Third, excess infrared radiation. A natural body only heats with the sun. A machine with a nuclear reactor or electronics would have anomalous hotspots emitting thermal radiation not explainable by a simple black body. So far, no anomalies reported, but that doesn't mean they don't exist. Fourth, light modulation. If the object rotates, its brightness varies. A lumpy rock changes brightness randomly. A ship with solar panels or symmetric components produces a regular, almost heartbeat-like light curve. We don't have this data. We're flying blind. In principle, the techno-signature hypothesis is fully testable. We just need simple observations. High-resolution spectroscopy. Infrared imaging light curve monitoring. If those observations are made and released, we can end the debate. But if they're not made, or worse, withheld, we're stuck in speculation forever. And that brings us back to the story's black hole missing data. Those gaps are where conspiracy theories breed. That's what we need to dissect next. What's normal and what's concerning? The truth is data never flows from telescope to public instantly. There's always processing quality checks, scientist exclusivity periods, and bandwidth limits. Space missions prioritize science, not public curiosity. Sometimes data from a flyby target gets bumped for higher priority observations. Annoying but normal. So when the online community noticed images from the Mars Reconnaissance Orbiter MRO in late October 2025 seemed delayed or missing, the rational first response was to check mundane reasons. But on social media, the first response is always they're hiding something. Let's see what normal really looks like. Orbiters like MRO operate on weekly command cycles. The process engineers upload a command sequence, the spacecraft executes, and data queues up. Data is never downlinked instantly. High-priority science like imaging a potential landing site gets pushed to the front. Photos of a comet flyby. They go to the back of the line. They can sit for weeks, sometimes months. The data is safe on the spacecraft's recorder, just not sent yet. Then there are safe mode events. If the spacecraft detects anything odd, a temperature spike, pointing error, power glitch, it automatically shuts down everything. It freezes, waiting for ground controllers to diagnose and fix. That can take days. If an orbiter went into safe mode in late October, then no photos were taken. End of story. Another reason, solar conjunction. When Mars passes behind the Sun from Earth's view, the communication link is completely cut. Solar radio noise scrambles any signal. During this time, missions go into near hibernation. No commands, no data transmission. And if that timing perfectly overlaps with 3-eye atlases, flyby mystery solved. These are predictable astronomical events. You can check the calendar yourself. Finally, data embargo, an open secret in astronomy. Mission teams get exclusive data access for 6 months or a year so they can analyze and publish first. This isn't shady. It's the rules, it's policy. If Mars orbiters only caught 3-eye Atlas as an opportunistic target, that data is almost certainly locked up right now. We'll see it, but not yet. There you go, backlog, safe mode, conjunction, embargo. All boring, but totally reasonable. But the real problem starts here. When agencies stay silent, when they don't issue statements, don't explain why data is delayed. That silence is where hypotheses take root. Silence always breeds suspicion. And with an object like 3-eye Atlas already so weird with its acceleration and color, any data gap instantly gets weaponized, pointed straight at a conspiracy. So when should we actually worry? Unexplained prolonged blackout, data vanishes for weeks, months with no official word. That's a red flag. Selective release. They publish images from around the time, but frames where 3-eye Atlas would have been in view are mysteriously missing. That suggests deliberate withholding, not randomness. Contradictory statements, NASA says one thing, ESA says another. That chaos is either disorganization or a clumsy cover. Right now, the status of the missing Mars frames is in the gray zone. Some say they're gone. Others say they were never scheduled. No official statement from NASA or ESA clarifies. Maybe a statement is coming. Or maybe there was never anything to say. We don't know. And that not knowing is the most frustrating part. But remember this core truth. Missing data proves nothing. It doesn't prove the acceleration is real. Doesn't prove it's a spacecraft. Doesn't prove a cover-up. It's just a loose thread. and in an investigation you have to pull those threads. Sometimes they snap, sometimes they unravel the whole story. Right now we're still pulling. Beyond the big shocks, acceleration, and color 3I, Atlas has racked up a whole list of smaller weird details. Taken alone, they're meaningless, but together they paint a picture that doesn't look like a normal comet at all. Sometimes the answer isn't in the blazing main signal, it hides in the noise and the details no one bothers to notice. Example: nickel emission. Preliminary spectroscopy reportedly detected traces of nickel. Nickel is metal. You find it in the iron cores of asteroids' fragments from planet formation. You don't find it in comets. Comets are ice, rock, and organic sludge. If this nickel detection is real, it's a massive compositional anomaly. Natural explanation. Maybe it's debris from a dead planet's core shattered long ago. Rare but possible. Alternative explanation. Nickel from an artificial structure. A metallic hull and engine heated to extremes at perihelion and vaporizing metal into space. Pure speculation, but it fits perfectly. Next, anti-tail. Some observers reported seeing a tail pointing toward the sun. Normally this is just an optical illusion. Large, heavy dust grains lag behind the orbit, and from a certain angle they look like a reverse tail. But here's the fatal contradiction. An anti-tail implies coarse dust, big grains. But the mysterious blue we see is produced by fine dust, tiny grains. So which is it? Does this object have both coarse and fine dust? Or is one of the observations wrong? Or is something entirely different going on? And finally, size. Estimates all point to it being a large object, possibly up to a kilometer, significantly bigger than Oumuamua. Size is critical because it determines mass, and mass governs acceleration from a fixed thrust. The bigger and heavier the object, the more massive the thrust needed to accelerate it. If the size estimate is accurate, and the acceleration is real, the required thrust or mass loss rate skyrockets to absurd levels, making the outgassing explanation more tangled than ever, instead of simplifying it. Conversely, this amplifies the appeal of the artificial hypothesis. A massive object could house more advanced technology, larger power systems, greater diversity of function, and a richer orbital history. 3I Atlas didn't blast straight from interstellar space to perihelion. Its orbit reveals mysterious prior encounters with Mars, Venus, or even Jupiter, possibly years, decades before detection. Those encounters could have bent its path, slowed its speed, altered its total energy. Many analysts call this orbital history too unusual and nearly implausible for a random interstellar object. Accurate assessment requires integrating the orbit to millisecond precision. Random interstellar objects can absolutely have complex histories if they enter the solar system at the perfect angle and speed. But if that history is too contrived, too ideal to deliver the object close to Earth in December 2025, suspicion is unavoidable. It starts to look like an engineered orbit, not a naturally evolved one. Let's restructure the problem through an imaginary matrix. Horizontal axis. Hypotheses: natural comet measurement error. Natural artifact, artificial object. Vertical axis. Evidence: paradoxical acceleration, blue color. Mass loss. Nickel anti-tail size. Orbital history, missing data. For each cell asked, does this evidence support or refute the hypothesis? Natural comet struggles with mass loss, paradox, and nickel. Maybe orbital history. Artifact explains acceleration but stumbles on color brightening anti-tail. Artificial object covers acceleration, color, nickel, even orbital history, but requires advanced technology and lacks direct evidence like visible structure or radio signals. No hypothesis dominates absolutely. Each has bright spots and shadows. That's the reality. We're suspended in fog. Data points in all directions. Every explanation requires assumptions, some weirder than others. So how do we proceed? Wait for new data. Observe relentlessly. Analyze deeper, widen the context, because 3I Atlas doesn't exist in a vacuum. It will explode into 2025. In a world where AI is accelerating data analysis at breakneck speed, where gravitational wave detectors are constantly uncovering bizarre black holes, where JWST is revolutionizing our understanding of cosmic composition and chemistry, the 3I Atlas story is just one piece in the grand puzzle of how we do science, communicate discoveries, and face uncertainty in the era of instant information and global networks. That's the direction we're heading next. The Big Picture Hidden Connections Profound Lessons Part 11. AI Computing Anthropology and Google TPU. October 23, 2025. With 3i Atlas just days from its Perihelion disaster, another event quietly exploded, fundamentally changing how mysteries like this are unraveled. Anthropic, the AI research giant, announced a strategic alliance with Google Cloud, unlocking access to TPUs, hardware specialized for planetary-scale machine learning. At first glance, this seems out of place with a mysterious object hurtling toward the sun, but the connection runs far deeper than the surface. What we're witnessing with 3i Atlas isn't just an astronomical mystery. It's an unprecedented convergence of modern science, social media, and superhuman computing power. The ability to process massive data has exploded in just a few short years. Work that once devoured months of PhD time writing code to stack images, refine orbits, run Monte Carlo simulations can now be done in hours by anyone with cloud access and the right algorithms. Orbital integration, solving gravitational equations to predict positions, once the domain of NASA or major observatories, has become a laptop game, or cheaper rent the compute for less than a fancy dinner. This is decisive for 3i Atlas. The public story exploded at light speed. Just days after Perihelion, the community was already analyzing orbits, calculating delta V, plotting revised paths toward Earth. The 50-day accumulated velocity change wasn't the product of an official research team after months of vetting. It was born from individuals on social media using open-source orbital mechanics software, cloud computing, and data from mission archives. The barrier between professional astronomy and public speculation has collapsed, and it's collapsing faster than ever. Large language models, the kind Anthropic builds, now assist scientific analysis in ways that were science fiction 2 years ago. Feed in raw data, ask it to detect anomalies, propose hypotheses, write code, even draft papers. The model hasn't replaced human experts. Not yet. But it amplifies them to astonishing levels. It lowers the threshold to turn curiosity into discovery. Someone wondering if 3i Atlas could hit Earth in December doesn't need weeks to learn orbital mechanics. They can ask AI to guide them, generate equations, run simulations, create visuals, all in an afternoon. This democratization has profound implications. On one hand, it's extraordinary. More eyes on the data means more chances to catch subtle signals mainstream science might miss. Citizen scientists have made real contributions, discovering planets, classifying galaxies, hunting asteroids. Expanding tools means opening new horizons of discovery. But the flip side of this revolution is the wide open door to false positives, pattern mismatches, and rumors spreading faster than verification. The 50-day delta V calculation is a living example, perfectly valid if you swallow the assumptions: constant acceleration, zero measurement error, thrust sustained evenly for weeks. Those massive assumptions would be red flagged instantly by an orbital dynamics expert. They'd run sensitivity analyses, tweak input parameters to see if the result collapses. But on social media, that calculation flew everywhere as gospel before any caveats could catch up. Once the straight-line Earth orbit graphic was posted retracting, it became nearly impossible. The story had its own momentum, sweeping the crowd along. The Anthropic Google Cloud TPU deal is a symbol of this tipping point. Computational resources for scientific analysis are now vast, distributed, and accessible to the point where anyone can own them. No supercomputer needed, no degree required. Just internet and a credit card. That's amazing, but it also means traditional scientific process, careful evidence gathering, peer review, independent replication is bypassed or compressed into timelines where rigor can't keep up. We're generating hypotheses faster than we can verify them. This isn't necessarily a disaster. Speed has its own value, especially when an object is barreling toward Earth, and decisions about observation or even emergency spacecraft launches are needed. But it demands a new kind of caution, a new cognitive skill. The public watching videos about 3i Atlas lining up with Earth needs to be equipped to distinguish peer-reviewed results from social media calculations. They need to see error bars, underlying assumptions, and alternative scenarios. That's where modern science communication becomes critical. The scientific feedback loop has fundamentally changed. Before, collect data, expert analysis, paper, press, public taking months or years. Now data released or leaked, or just from a personal telescope. Instant parallel analysis. Professional teams, amateurs, AI investigators all dive in at once. Results explode on social media. Hypotheses evolve in real time. The public isn't waiting for the official story. They're co-authoring it with AI as a powerful catalyst. Machine learning accelerates every step image. Processing automatic anomaly. Detection superior pattern recognition. Hypothesis generation large language models suggest directions humans never thought of. Simulations run thousands of scenarios in the time it once took for one. The technology empowers massively, but it's also overwhelming. We're at a transitional crossroads. The tools have outpaced the institutions. Public data available compute, but the frameworks for validation and contextualization are still sluggishly adapting. 3i Atlas has become a living lab for this new reality. Observations from official spacecraft processed by NASA, but the analysis results leaked. Now, a flood of parallel hypotheses. Conservative unusual comet need more data. Speculative artificial object intentionally targeting Earth. Skeptical measurement error. Bugs social hype. Each camp picks its data, its analysis, its momentum. AI infrastructure makes it all possible simultaneously. So when we talk about 3i Atlas, we're not just talking about an object in space. We're talking about how science operates in the era of distributed computing, instant communication, AI analysis. The next big astronomical discovery will unfold in this exact environment, faster, more public, more chaotic, and at risk of simultaneously delivering historic breakthroughs and serious misunderstandings. The Anthropic TPU deal is just one milestone on that journey. The infrastructure is forming. The big question: will our collective capacity for critical thinking, distinguishing signal from noise, maintaining accuracy amid breakneck speed, adapt in time? Other fields are facing similar challenges and may offer lessons. LIGO Virgo Cagra announced a slew of new black hole mergers from the O4 observing run, including candidates for second-generation black holes not born from stellar collapse but from mergers of prior black holes. At first glance unrelated to a mysterious comet, but the way the gravitational wave community operates is a sharp contrast to the 3i Atlas chaos. Gravitational waves, ripples in space-time from accelerating mass, typically arise when black holes or neutron stars spiral into merger. LIGO consists of two 4 km L-shaped detectors in the U.S. Waves passing through stretched space one way, compress it the other, creating oscillations smaller than a proton's width that lasers still measure. The extraordinary precision has opened a completely new window on the universe. But the key isn't just detection, it's the pipeline. When LIGO catches a candidate, a public alert goes out in minutes, no waiting for peer review, no delay. The alert reaches astronomers worldwide who immediately swing telescopes to hunt for electromagnetic counterparts, gamma rays, optical flashes. This is multi-messenger astronomy, gravitational waves combined with light observation, effective thanks to transparency, speed, collaboration. The alert includes uncertainty, sky maps, preliminary classification, black hole, neutron star, or oddball. Raw data is public immediately. Anyone with skills can download and reprocess. Initial classification may change, but the community accepts it early. Alerts are just sketches. Refinement takes time, and transparency about uncertainty is worth more than delayed certainty. Independent verification is baked into the DNA of the gravitational wave system. Put it on the scales with 3i Atlas observations from spacecraft processed by NASA and agencies. But results leak through unofficial channels, social media, flash announcements, rumors. There's no coordinated public alert system for interstellar objects. No immediate raw data release. Just scattered fragments, vast gaps filled by speculation. The gravitational wave community has found the formula: fast science in front of the public while keeping the blade of accuracy sharp. The interstellar community hasn't, at least not yet. Why does this matter? Anomalous phenomena demand multi-angle lenses, overlapping independent analysis, ruthless cross-checking. If 3i Atlas is truly showing non-gravitational acceleration, the only way to nail it down is multiple teams reprocessing the astrometry, comparing results, quantifying systematic errors. That's the gravitational wave routine LIGO chirps Virgo, and Kagra instantly cross-check. 3 detectors agree, confidence skyrockets. 1 alone, skepticism explodes. The false positive prevention is built in. The second-generation black hole discovery illuminates further bizarre entities born from prior mergers with masses and properties beyond theoretical bounds. The community doesn't rush to proclaim new physics. They model the signal compared to general relativity, set extraordinary evidence thresholds for extraordinary claims. 3i. Atlas, if truly breaking natural deserves the same yardstick. No data gap conspiracies, no guesswork, but transparent multi-team public data layered verification. The gravitational wave model proves this is possible even for transient phenomena. LIGO alerts in minutes while keeping science intact. The principles apply to asteroid comet surveys. Imagine the future next interstellar object detected. Hours later, public alert with spectrum brightness preliminary orbit. Telescopes worldwide swing in unison. Spacecraft are retasked. Raw data dumped straight to public repositories. Experts, amateurs, AI all dive in. Hypotheses spawn, clash, refine, or die on the altar of evidence. Public, fast, rigorous all at once. This isn't science fiction. It's how gravitational waves operate today. The infrastructure exists. The culture exists. It just needs adaptation. Second-generation black holes remind us the universe is inherently weird. Processes we're still groping to understand. Phenomena that stun us even with equations in hand. Weird, artificial. Distinguishing natural weird from artificial weird demands sharp data and cold analysis. Rushing to conclusions either way is scientific suicide. Lessons from LIGO 04 and 3i Atlas Perihelion, 2 parallel branches of science. One has reconciled transparency, collaboration, instant public access with steel-clad rigor. The other is still mired in isolated speculation. Those norms, those practices are a map not perfect, but working to guide how we greet the next interstellar visitor, especially when they do things we don't yet understand. Because the horizon of what's out there is blooming like never before thanks to JWST and its kin. That explosion is reshaping how we interpret 3i Atlas down to depths we're only beginning to touch. October 2025 dropped another bombshell, at first glance unrelated to the bizarre interstellar object near the Sun. The James Webb Space Telescope, humanity's most powerful infrared machine, announced methanol, ethanol, and countless complex carbon compounds in extragalactic environments billions of light-years beyond the Milky Way. Molecules once tied to prebiotic chemistry now present in environments utterly alien to the solar system. The profound message: some foundational chemical processes are universal enough to cross galactic boundaries. JWST operates in infrared, capturing heat and light stretched by cosmic expansion or cooling, opening doors to exoplanet atmospheres, distant galactic composition, star-forming regions. From its first images in 2022, it has continuously rewritten cosmic chemistry textbooks. The October 2025 discovery is just the latest chapter, and it could forever change how we view 3i Atlas. Why is JWST the key to 3i Atlas? Because the very anomalies giving us headaches, unusual nickel emission if real. The blue color, the absurd mass loss ratio spectra implying bizarre composition, all become less freakish when placed in the broader cosmic context. Our familiar comets formed 4.5 billion years ago, in the solar system orbiting predictably. But 3i Atlas is an outsider, possibly from a star system with wildly different formation history, metal ratios, pre-planetary conditions. JWST is expanding the normal envelope at dizzying speed. Methanol, ethanol, complex carbon compounds appearing in extragalactic environments where metallicity, radiation, evolutionary history differ fundamentally. If complex chemistry can bloom in harsh corners of the universe, the possible ingredient list for objects is wider than we thought. An alien interstellar object might just be alien relative to our local sample. The solar system isn't the cosmic standard. Nickel supernova product usually locked in planetary cores or primitive metallic grains. Icy outer comets rarely carry free nickel, but if 3i formed in a metal-richer protoplanetary disk where supernova enriched differently, or ice contaminated with metal. In ways we haven't seen, nickel emission suddenly fits within the expanded natural spectrum. Still rare but plausible. The blue color gets recontextualized too. Fine dust grains, specialty ice molecules born under exotic conditions could alter scattering fluorescence. JWST proves molecules once thought to exist only in right environments appear in completely different contexts. Extrapolate interstellar objects could carry chemistry we've never encountered simply because they come from a different branch of cosmic evolution. This doesn't solve everything. The non-gravitational acceleration, the mass loss paradox still hang. But it shifts the weird baseline. Before JWST, the cosmic chemistry catalog was limited by older telescopes, nearby sources. Familiar spectral lines. JWST's infrared opens the cold, distant, diverse. Every new molecule in a far galaxy is a brick expanding the periodic table of cosmic possibility. There's philosophy too. The deeper we dive, the smaller our observational sample seems. One detailed planetary system, a few dozen probes, thousands of indirect exoplanets, and exactly 3 confirmed interstellar objects. Oumuamua 2017 cigar-shaped tumbling non-gravitational acceleration no coma. Borisov 2019 a comet so normal it was disappointing. Atlas 2025 a fresh batch of anomalies. 3 data points aren't statistics. Oumuamua made us think interstellar visitors are always weird. Borisov said not necessarily. Atlas opens parentheses again. We don't know normal for interstellar travelers because we've barely met any. JWST doesn't solve the puzzle but sets the stage. The universe is chemically diverse. Local expectations are fragile. Weird might just be unfamiliar. Context cuts both ways. If 3I's composition fits snugly in JWST's expanded natural spectrum, the artificial argument weakens. Conversely, if even with new data the acceleration color mass loss paradox remain outliers, the artificial hypothesis sharpens. Context doesn't give answers, it gives sharper questions. And those questions will be answered by new tools. Transient anomaly hunting tech is exploding in parallel with discovery. Late October 2025, the University of Birmingham announced on Science Daily a new generation of ultra-compact gravitational wave detectors, not km-long arms like LIGO, but lightweight devices. Rapid deployment targeting frequency bands currently missed. At first glance, GW physics internal, but really a symptom of a bigger trend. Networks of specialized distributed sensors supplementing giant observatories, the exact formula needed to catch the next interstellar visitor before speculation outruns data. Gravitational waves are a cosmic symphony with diverse frequency bands, each note reflecting distinct origins. Current LIGO and Virgo are delicate violins resonating at high frequencies from tens to thousands of hertz, catching the final chirps of stellar mass black holes or neutron stars spiraling into merger. But the universe hides deeper bass notes. Millihertz waves from billion solar mass black holes slow dancing at galaxy centers. Intermediate frequencies from intermediate mass black holes, the teenagers of the black hole world. And ultra-high frequencies possibly from primordial sources, the early universe or unknown physics. To hear the full score, we need a diverse orchestra, not just one giant instrument. The University of Birmingham's ultra-compact detectors are those new instruments. They don't need 4-kilometer laser arms, just shoebox-sized, using quantum sensors, atomic interferometers, or superconductors. Some designed to float in space, forming constellations millions of kilometers apart, turning the void into a giant interferometer. The core message is clear: bigger isn't always better. Sometimes you need difference. Sometimes you need numbers. A network of compact detectors can do things a single massive machine can't dream of. Take this mindset to optical and infrared astronomy, where we hunt transient visitors like asteroids, comets, and especially interstellar objects. We have the grand organs JWST Hubble 8 to 10 meter ground telescopes, but they're expensive schedules packed and not built for instant reaction to surprise targets. When 3I Atlas swept into the inner solar system, data mostly came from solar observatories that caught it by chance, like a passerby snapping a blurry photo of a strange car speeding by with no plates or papers. No dedicated system, no contingency plan, no network. The result, scattered data fragments, vast gaps filled by speculation. Imagine a different future. A network of dedicated small satellites scattered across the solar system like a cosmic nervous system. Dozens, even hundreds of CubeSats, each the size of a shoebox or loaf of bread, carrying compact telescopes, mini spectrometers, infrared sensors, high-resolution cameras, some anchored near Earth in LEO or GEO, some floating near the Sun in heliocentric orbits from 0.3 to 0.7 AU, some stationed at Lagrange points L4, L5 of the Earth-Sun system, or Sun-Jupiter, where views are wide, stable, low noise. Each satellite isn't powerful alone, but connected they form a super-observing system, continuous multi-angle instant response. When an interstellar object enters the coverage zone, the network activates instantly. Immediate detection from multiple satellites, at once eliminating noise from the start. Multi-angle measurements deliver parallax accurate to arcseconds, mapping a complete orbit in hours. Continuous spectroscopy tracks composition changes in real time. Nickel spiking ice, sublimating anomalous fluorescence, precision photometry records. Brightness, color, reflectivity across wavelengths. Multiple viewing angles. No waiting for JWST to pivot. No hoping for clear ground skies. No fighting for observing slots. Redundancy, diversity, and speed become the standard. This tech isn't science fiction. CubeSats have proven scientific capability through missions like MinXS's, imaging the Sun, CIS, measuring radiation, or Astoria, doing planetary spectroscopy. Launch costs down 90% thanks to reusable rockets like Falcon or Starship. Laser links and high bandwidth data transmission are commercial. Onboard AI autonomously detects, classifies, prioritizes. Observation sends alerts to Earth in minutes. The only missing piece is funding and organizational will. 3i Atlas is the perfect wake-up call. The 4 arc-second acceleration deviation could have been confirmed or debunked by independent measurements from 3-4 different satellites. The blue color shift could have been tracked continuously in infrared UV invisible. Nickel emission mass loss ratio could have been constrained or confirmed via real-time spectroscopy from multiple angles. Orbital history could have been mapped more accurately from Lagrange points. Instead of arguing over patchwork data, we'd have a complete multi-dimensional, undeniable picture. Moreover, time is gold with interstellar objects. They move fast, lingering only a few months in the solar system before vanishing into the void. 3i Atlas appeared early in 2025 and will depart by year's end. The Perihelion window, just a few days, is when activity peaks, outgassing, brightening acceleration. A distributed network ensures we miss no phase. Entry phase, initial description, pristine composition. Perihelion maximum activity testing, non-gravitational thrust. Exit phase, cumulative effects, post-solar energy orbital changes. Each stage is a unique puzzle piece and the network captures them all. This distributed philosophy is spreading across astronomy. Radio uses interferometers like VLBA or SKA, linking thousands of small dishes into one giant telescope. Optics explores robotic telescope arrays like Everscope or Black Gem. Gravitational waves plan LISA 3 spacecraft 2.5 million km apart, or Tianqin de Sigo. The future isn't centralized, scarce machines, but distributed collaborative systems at the hardware level. For interstellar objects, this is a strategic revolution. Currently, we're in passive reaction mode. Late detection equipment scramble fragmented data. Opportunistic science limited by luck. With a dedicated network, we shift to continuous, proactive mode. Always watching tools, ready data flooding in. When another 3i Atlas appears and starts acting weird, we won't wonder if the measurement is trustworthy. We'll have redundancy. We'll have cross-checks. We'll have confidence. Cost isn't the barrier. One JWST costs $10 billion. A network of 50 to 100 dedicated CubeSats runs $200, $500 million, 20 times cheaper, yet delivers continuous coverage and higher survivability. One satellite fails. Replace it in months. One big telescope fails, mission over. With a network, degradation is gradual and controllable. The lesson from Birmingham's ultra-compact detectors is clear: innovation isn't about bigger or more sensitive, but redesigning observation architecture. Using existing tech, small satellites, AI laser comms, reusable launches, we create capabilities that never existed non-stop. Observation, instant reaction, multi-dimensional data, speculation eliminated by evidence. With 3i Atlas, we can't answer definitively: is the acceleration real? Is the color anomalous? What's the mass loss ratio? But next time when another interstellar visitor knocks, we'll be ready. And as we close this investigative journey, look at the big picture. The 3i Atlas story isn't just about an object in space. It's about a new era of science, AI, accelerating analysis, social media, democratizing speculation, the public co-writing discovery history and observation infrastructure, shifting from centralized scarcity to distributed abundance. We're witnessing the evolution of human knowledge, faster, more chaotic, but also fairer and more powerful than ever. When the next interstellar visitor arrives, we won't stand empty-handed. We'll have eyes everywhere, ears in every frequency, and data enough to distinguish natural weird from artificial weird before the story spreads. This story is no longer about an object floating in space, but about us. How a civilization is learning to face the anomalous way evidence and hold the line between the known and the unknown, in an era where information moves faster than verification. Summer and fall 2025 saw an explosion in the AI world. Anthropic, OpenAI, Google, xAI, and countless others continuously releasing newer, more powerful, smarter large language models, each closer to human-like reasoning. They don't just write texts or translate languages. They write code, analyze astronomical data, generate hypotheses, even draft scientific papers in seconds. That capability has completely transformed how we approach science, and 3i Atlas is the most vivid proof. What unfolded in recent weeks with 3i Atlas isn't just an astronomical phenomenon, it's a massive socio-scientific experiment. When social media analysts, from students to engineers to space enthusiasts, ran delta V calculations, plotted orbits showing the object might align with Earth in December 2025, created visuals, explainer videos, and shared them millions of times, 90% of them used AI. Large language models suggested equations, wrote Python scripts, auto-stacked images, ran Monte Carlo simulations, even proposed physics scenarios they hadn't thought of. The barrier to sophisticated science has collapsed. You don't need a PhD in orbital mechanics anymore. Just curiosity, a GitHub account, and a free or few dollars a month AI model. This is a revolution in democratizing knowledge and a ticking time bomb. The extraordinary part: citizen science has never been this powerful. Thousands of eyes, hundreds of brains, millions of parallel calculations, checking official claims, spotting errors, proposing new directions. An individual in Vietnam can download NASA archive data, use AI to refine an orbit, and catch an anomaly the official team missed due to overload. But the downside is just as sharp: traditional controls, peer review, proven expertise. Institutional affiliation are completely bypassed. A calculation that sounds plausible, a slick graphic, a clickbait video titled NASA hiding the truth about 3i Atlas can spread to millions before any expert speaks up. And once the error is out, correction is nearly impossible. Crowd psychology, engagement-driven algorithms, and human love for complete stories turned a 4-arc-second deviation into proof of an artificial object targeting Earth. 3i Atlas became the perfect mirror for this chaos. Claims of non-gravitational acceleration, missing Mars, images in the data Earth alignment scenarios, all exploded on social media, amplified by recommendation systems that prioritize emotion over truth. Sensational videos racked up millions of views. Provocative posts spread like wildfire. Meanwhile, raw data error bars, model assumptions, reliability warnings all drowned in the information flood. Not from malice, not from conspiracy, but simply because that's how the 2025 digital ecosystem works. Speed beats accuracy, emotion beats reason, story beats data. So what lessons do we take from this storm? First, transparency is the strongest weapon. If NASA, ESA, and the agencies handling 3i Atlas data had released everything from the start, raw frames, calibration files, processing pipelines, metadata observation logs, the community could have verified or debunked every claim in hours. Official information gaps are fertile ground for speculation to sprout. Gravitational wave astronomy has proven this works. LIGO releases raw data in minutes, invites thousands of scientists to reanalyze, and credibility multiplies. Transparency doesn't weaken authority, it strengthens it by turning the public into allies, not adversaries. Second, we need a new form of science communication honest about uncertainty. Every measurement has error bars. Every model rests on assumptions. Every conclusion is provisional. But in the storytelling race, those nuances vanish. A 4. Arc-second deviation becomes NASA confirms course change. Then interstellar object deliberately targeting Earth. Then we're about to be hit. Each step loses integrity. AI can help here, auto-generating plots with error bars, flagging assumptions suggesting alternatives. But it can also harm. A model can spit out dozens of plausible explanations without knowing which is most viable. Write analysis code but hide subtle bugs. Draft papers but hallucinate citations. Powerful tool but demands responsible human judgment, especially when stakes are high like a potential Earth-impacting object. Third, we need to cultivate cognitive humility. We don't know what 3i Atlas is. We have data. We have hypotheses. We don't have certainty. And that's perfectly fine. Science thrives in uncertainty. Saying we don't know yet but we're investigating is a powerful, honest scientific statement. But it doesn't sell ads, doesn't trend, doesn't hold attention. Social media news, the news cycle, all favor conclusions, answers confirmation whether just a comet or alien probe. The in-between state ambiguity doesn't satisfy, but that's exactly where real science happens. The 3i Atlas story is a mirror of how we process information in 2020's massive data more available than ever. Analysis tools accessible to anyone. Instant global communication unbounded, but human cognition wetware evolved for 50-person hunter-gatherer bands. Local threats campfire stories is still trying to process AI-generated orbit plots, deepfake videos, and rumors spreading at light speed. That's a dangerous mismatch. So what does it mean for 3i Atlas? The object will follow its orbit. The December 2025 Earth flyby will happen whether at the original predicted distance or shifted by accumulated delta V. There will be more observations or there won't. Data will be released or trickle out. The story will end with a natural explanation, a measurement error, or something beyond current understanding. We don't get to write the ending. We only get to observe, analyze as best we can, and learn from the process. If there's a call to action, it's this: release raw data immediately. Teach the public to read error bars. Use AI to accelerate verification, not spread speculation. Embrace uncertainty as part of science. Because the next time another interstellar visitor arrives, and it will maybe in years, maybe decades, we need to be ready not just technologically but in mindset, culture, and responsibility. 3i Atlas isn't just an object floating in the dark between stars. It's a final exam for a civilization learning to mature in the era of hyperspeed information where data floods, AI amplifies, and truth can be distorted in a single click. We're still mid-exam, and there's no sign of recess coming. Start with concrete action demand. Absolute transparency from data handling organizations. NASA, ESA, JAXA, major observatories, all must release raw data processing pipelines, metadata and observation logs as soon as possible, not after months of review. No more information gaps, because those gaps are where rumors, conspiracies, and misunderstandings grow. Transparency isn't conceding to the public. It's the strongest weapon to protect science. Support efforts to build better observation infrastructure. Not single $10 billion super telescopes, but networks of small, distributed, dedicated satellites. Hundreds of CubeSats spread across the solar system from near-Earth to Lagrange. Point solar orbits to the outer edge. They'll observe continuously, react instantly, deliver multi-angle, multi-wavelength data. Eliminate speculation with evidence. This isn't science fiction. It's science we can do today, just needs will and funding. Sharpen critical thinking skills for yourself, your kids, your community. Learn to read error bars. Learn to ask what assumptions underlie this result. Where's the raw data? Who verified it? In a world where AI can write a scientific paper in 30 seconds and social media turns a wrong calculation into alien proof, the ability to pause, check, and doubt is the last human superpower left. And above all, hold on to wonder. Because even if 3I Atlas turns out to be just a normal comet with a bit of odd nickel blue from scattering acceleration from measurement error, the fact that we can see it from outside the solar system, track it, analyze it, argue about it, imagine what it could be, is already a triumph of human intellect. The universe is vast. It holds things we've never seen, phenomena we've never imagined, and maybe, just maybe, evidence of another civilization. 3I Atlas might be that evidence, or it might not. But either way, the questions it raises, the conversations it sparks, the gaps it exposes in our knowledge infrastructure, and even how we think, all are priceless. We learn as much from mysteries that turn out mundane as from those that rewrite textbooks. Both remind us we're still children before the cosmos. So stay curious, stay rigorous, stay open to both natural and alien possibilities. The file on 3I Atlas isn't closed. There will be new data, deeper analysis, long nights staring at the sky wondering, and whatever the final answer, reliable or revolutionary. The journey to get there is the most important part of the story, so keep watching, keep asking, keep verifying, and remember, in the age of AI, social media, and instant information, our most powerful tool isn't in the cloud, isn't in the telescope, but between our ears. Use it well.